This video continues our work regarding areas under graphs. The questions we've done so far, we've been given the graph, we've had to work out the definite integral and look at our terminals, look at where we put our terminals and work it out. Here we go a step further. We've actually got to draw a graph, and we needed some skills to do that, of drawing the graph without a calculator and with a calculator. So in this video I'm going to look at both skills and probably focus a little bit more towards the end with using the calculator. So let's get underway. Here's the first example. Sketch the graph of the function. I've written that twice. There you go. Sketch the graph of the function g of x equals 3 minus x, 2 plus x. Find the area bound by the x-axis and the graph of the function. Alright, so we have to graph this function, and with area questions such as this, the only relevant things really are the shape of the graph and the x-intercepts. The turning point and the y-intercept here are not relevant because we're looking at the area under the graph. So when we find x-intercepts, we make y equals 0, in this case g of x equals 0, and we solve. And if we solve here, we get the two solutions, x equals 3 or negative 2. So they're going to be our x-intercepts, 3 or negative 2. So we can now draw ourselves a graph. The other thing to mention here is that the shape of the graph is going to be, a dominant term is going to be negative, so the shape of the graph will be that sad face type shape there, because if you times that out, we might do that. G of x would actually equal 3 times 2 is 6, plus 3x, minus 2x is plus x, and you've got minus x squared. So we know from when we did our work on parabolas, quadratic graphs, that a negative x squared term gives us that upside down shape there. So there are a couple of basic things we know. Time to draw the graph. So I've drawn in here. As I said, it doesn't really matter where our turning point is. Can we just draw it up there? So if we draw the graph like so, then the area, if we just go back to the question, find the area bound by the x-axis and the graph of the function. So our x-axis, okay, we know what that is, and our function is here. So we're looking at, if I just put some shading in here, we're looking at that area there, the area under the graph bounded by the x-axis. So there it is there. Now, the question is really framed up very similar to the ones we've been doing. And the definite integral we want is the integral, and we put our right terminal top there and our left terminal at the bottom, and our function. Now we can do a couple of things here. Probably prefer, it's really good here to use the version where it's multiplied out. So 6 plus x minus x squared. So 6 plus x minus x squared dx. Just need to fit that in there. So dx, there we go. So that's the integral we're looking at. So we need to integrate this then. Square bracket, so we get 6x plus x squared on 2 minus x cubed on 3, and our terminals are 3 and negative 2. So then we substitute in, as we usually do, for 3 and neg 2. I'll just pause while I do that. Okay, so I've inserted the numbers 3 and negative 2. Oops, I did 2, not negative 2. Picked it up myself. There we go. And now we can expand the brackets. So it equals 18 plus 9 on 2 minus 27 on 3 minus 6 times neg 2, neg 12, negative 2 squared is 4 on 2 is plus 2, negative 2 cubed, there, we've got negative 8, and we've got a negative there as well, so negative 8 is plus 8 on 3. Tidy things up here now, we get 9 plus 9 on 2 minus 9 minus, so we've got negative 12 plus 2 plus 8 on 3. We might just leave it at that for the moment, and then we'll get everything together in the next line. Alright, time to remove brackets. So we get a 9 and a neg 9 there, and cancel each other out. So we get 9 on 2. So we get a minus situation, plus 12, minus 2, minus 8 on 3. Silly mistake I just made here, sorry. That was 18, wasn't it? Where I put 9 there for. So we've still got 9 plus 9 on 2 plus 12 minus 2 minus 8 on 3. So what we might do here, might just get all the whole numbers together. So 21 minus 2 is 19 plus 9 on 2 minus 8 on 3. Everything must be now over a common denominator, which will be 6. So we get 19 as a denominator of 6 is, let me see, it's 114 over 6, plus 9 over 2 is the same as 27 on 6, minus 16 on 6. So that's going to be a grand total of 125 on 6, which is 20 and 5/6 square units. As you can see, there's quite a lot of mucking around without a calculator. But of course, in our exam, they could be fair game, a question like that. But let's now look at another approach by using our calculator. So here I've drawn on our TI Nspire the graph of 3 minus x, 2 plus x. And I've set my axes so that it's a nicely proportioned graph, and I can see the whole graph, and I haven't got a lot of wasted space. And we've talked a bit about that at the start of the year, about how to set graphs using your window screen to make sure, as I said, your graph is well proportioned. So there it is. So of course the area we're trying to find is this area here. Can't shade it all in, but we could see that from the last question. That was what we had to work out. So the good thing about the calculator, we don't have to worry about expanding 3 minus x, 2 plus x. Now we know from our graph here, the area that we're trying to find, we know that our terminals are going to be negative 2 and 3. We can see that from the graph. There they are, there and there. So that's our terminals. We know that it's above the axis because the area that we're trying to find is there. So we can put in our definite integral, 3 neg 2, 3 minus x, 2 plus x, and you can see, simple as that, we get the same answer as what we got using our method without the calculator. So that's just a contrast there between, there's a lot of working out there if you haven't got the calculator, but with the calculator, TI Nspire, if you know what you're doing, you know the area you're trying to find, you can do your graph well on the calculator, you know how to do integrals on the calculator, not a problem. So let's look at this next one, which we're going to do with the calculator. Find the x-intercepts of y equals sine 2x over the domain 0 to 2 pi. Calculate the area between the x-axis and x equals 0 and x equals pi. Right, so what I've done there is I've drawn the graph, I've set my axes from 0 to 2 pi. You can see this 6.28 here, which is 2 pi, okay, and 3.14 there, that's pi. So there I've drawn the graph of sine 2x, okay. And what we might do is just mark in pi there and 2 pi, and we know that that's pi on 2, and that's 3 pi on 2. So there we go. Okay, so calculate the area between the x-axis and x equals 0 and x equals pi. So the two areas that we want here are, if I just shade them in, this area here, like so, there we go, and also this area here. Okay, so they're the two areas that we want. My shading's not great there, but you get the idea. Between 0 and pi. So just read the question again. Calculate the area. Here it is. Calculate the area between the x-axis and x equals 0 and x equals pi. So we've got two areas. We've got one above the axis and one below the axis. So here's our two integrals. So looking at the area above the axis, 0 is our left-hand terminal, pi on 2 is our right-hand terminal. So you can see there I've got left over right, and I'm putting in the calculator. For the below axis, we've got pi and pi on 2. Now, remember we talked about those different methods about what you do to the terminals when it's under the axis. And I like to reverse the terminals. So I have the left one on the top there and the right hand one on the bottom. So I've set it up there. So once again on the calculator, I've just set it up in one question. The integral plus the other integral, we've got to add the areas together, and the total area there is 2. This is an interesting question. It says find the shaded area. And you'll notice the shaded area isn't bound by the graph and the axis. Okay, it's in a different spot. So we're used to, at the moment, if I just mark it in green, we're used to finding this area, the area under the graph, okay, which is that one there, and I might leave that shaded in because we might need that in a moment. We're actually asked to find that orange area. But we know from current methods how to find that green area. Okay, and I'll just mark that in again here. There we go. Now, I might just pause here and think, how could we work out, it might be easier to look at in the large diagram, how are we going to work out that orange area? Okay, how are we going to do that? So I'll pause it there. We might pose that to yourself if you're watching this at home, or we might have a chat about it in class now. Okay, so we've got this point here, 2, 4. So that would indicate that that coordinate there is y equals 4, 0, 4. So we've got actually a rectangle there. I probably haven't drawn it very much to scale. It looks like a square, but we've actually got a rectangle there. And so if we took the green and the red area, so that total area of, I'll just write A1 there for the moment. If we took that total area, it would simply be the area of a rectangle. It would be 4 length times width, which is 2, equals 8 square units. Okay, now if we work out the green area, which is the area under the graph, and subtract it from 8, we'll get our targeted area, which is the orange area here. So let's look at that. What would the green area be? Well, area under the curve, it would be the integral, right-hand terminal over left, of x squared, equals x cubed over 3 is our definite integral here, 2 and 0. The second term will be 0 when we put x in. We substitute 0 into x. So we're going to get 2 cubed on 3 minus 0 cubed on 3 equals 8 on 3 square units. Right, so hence our total area will be the area of that rectangle I was talking about, which is 8, minus the area under the curve, which is 8 on 3. So that's 24 on 3 minus 8 on 3 is 16 on 3 square units. Okay, so that gives us a show now doing exercise 9G. We'll give it a go.